Okay, welcome. I'm going to talk about the security of the Fiat-Shamir transformation in the random oracle model. And this is joint work with Jelle Don, Chris Mayens, and Chris Schaffner. So first, I want to briefly recall what's the Fiat-Shamir transformation. For that, I have to briefly recall what's the Sigma protocol. So Sigma protocol is an interactive proof for proving membership of some instance X without revealing a witness. And what makes such an interactive proof, a Sigma protocol, is this three-round structure with the second message being a randomly chosen challenge. And throughout this talk, I'm always going to assume that this challenge is chosen from a large set. This can always be achieved just by repeating the protocol in parallel. Now, the security properties we usually care about are soundness or proof of knowledge in the context of a dishonest prover, or some flavor of zero knowledge in the context of a dishonest verifier. Now, all these notions can come in different flavors, ranging from computational to statistical. And in this talk, I'm mainly going to focus on the security properties in the context of a dishonest prover. I'm not going to talk about zero knowledge. Okay, so then a Fiat-Shamir or the Fiat-Shamir transformation is a way to transform such an interactive proof into a non-interactive proof by not having the verifier choose the challenge, but by setting the challenge to be the hash of the first message A. Well, for some technical reason, you should actually set the challenge to be the hash of the instance and the first message, but I'm going to skip over that in this talk here. So this then turns this interactive proof into a non-interactive proof. Now, by a small tweak to this construction, by actually setting the challenge to be the hash of A and some additional arbitrary message M, one can actually understand the interactive proof then as a signature on M. So this gives us a signature scheme, Fiat-Shamir signature scheme. And, well, classical results tell us that this design principle works well. Namely, we know that if the underlying Sigma protocol is secure, then the Fiat-Shamir transformation is secure in the random oracle model. And you can plug in your favorite notion of security, ranging from computational soundness to statistical proof of knowledge, and the claim is that, well, the security is preserved. Now, from this, it's not too hard to conclude that if the underlying language is hard and the Sigma protocol is a proof of knowledge, that also this Fiat-Shamir signature scheme is secure, well, again, in the random oracle model. Now, for later, it's going to be useful to look into the proof of this result, of the security of the Fiat-Shamir transformation. Now, the proof is a standard proof by reduction. So we start with a dishonest prover P attacking the attacking the Fiat-Shamir transformation in the random oracle model, and we transform it into a prover P prime attacking the Sigma protocol and succeeding with a similar success probability. So the way this works is that you choose one of these queries uniformly at random, and you sort of steal the query here and output it as the first message in the attack against the Sigma protocol. And then when you receive the challenge here, from there on, you use what we call a reprogrammed oracle in order to answer your oracle queries, where the reprogrammed oracle answers as the original oracle before, except at that one point A prime here, where we set the hash to be the challenge that we got here. And then at the very end, right, we sort of steal the response Z here as the response that we output in the attack against the Sigma protocol. And then it's not too hard to see. I'm not going to go too much into the details here, that if the P outputs here as part of his proof coincides with the query that we stole here, then P prime is as successful as P, and the probability that this happens is roughly 1 over Q. The reason being that in order to come up with a valid proof down here, he needs to know the hash of A. The only way he can learn the hash of A is to make a query to the oracle. So with probability 1 over Q, we're going to catch him. Okay, so if the dishonest prover is equipped with a quantum computer, then in real life, where the hash function is an explicitly known hash function, then he can compute this hash function in quantum superposition. So in order for this random oracle model to be minimally meaningful, realistic, also in the random oracle model, we have to give the prover this power of being able to make superposition queries to the oracle. And then, of course, the big question is whether these classical results still hold when we give the prover this additional power. And, well, the answer is non-trivial. If we try to recycle the classical proof, then you immediately run into trouble. The problem is that now the query that we want to steal here is the quantum state, but we still have to output sort of a classical message here as the first message in the Sigma protocol. Now, the obvious way to get from a quantum state to a classical message is by performing a measurement, but then a measurement disturbs the state, and then it's sort of not clear to what effect this is going to disturb or affect the prover. In the worst case, he realizes that his query got measured, and he aborts, and he doesn't produce a proof at the end, and then we're stuck here in producing this response here. So what has been known about this problem, so it was known that another transformation, referred to as the Unruh transformation, which achieves the same task, is secure, but unfortunately this transformation is less efficient, so we rather use the Fiat-Shamir transformation. Also, what was shown by Dominic is that if the Sigma protocol is statistically secure, then the Fiat-Shamir transformation becomes is statistically sound, then the Fiat-Shamir transformation becomes computationally sound. So in a way, soundness is preserved, but there is this degradation in the quality of soundness, if you wish. In particular, nothing was known about what happens if the Sigma protocol is computationally sound, or what happens if you care for proof of knowledge property, which, as a matter of fact, is important in the context of signature schemes. Yes, Dennis?
So when you all of a sudden computational soundness turns out, but there's no assumption involved. It's just against only.
So yeah, when you speak about computational soundness of the Fiat-Shamir transformation, I mean that I'm going to limit the number of queries, the oracle queries that the prover can do, but otherwise he may have arbitrary computing power. But of course, I have to limit the number of oracle queries that he makes. As a matter of fact,
It's also true in the classical setting, right? The statement is not improved upon. Even in the classical setting, in the same way, if you start with a statistically sound protocol in Fiat-Shamir, you get computationally sound in exactly the same way. I mean, exactly the same notion.
So classically, what you get is if you start with a statistically sound protocol, you get a Fiat-Shamir transformation is and also statistically sound. Again, by understanding statistically sound, secure against the prover that is limited in the number of oracle queries that he can make, but unlimited in the local computation that he can do.
So here, so when you say right computationally sound here, you mean something else than in the classical setting?
Yes. 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 So here I also limit the local computational power of the prover. I think.
Problems that like LWE or some things that if you break.
Well, yeah, I'm not entirely sure. I mean, I know that's sort of the result that Dominic claims, and he actually made some claim that you need to start with a statistically sound Sigma protocol, and that you won't get this kind of result if you start with a computationally sound protocol. There were also some negative claims about the possibility of proof of knowledge property, but it turns out that actually we can recover the classical result as it is, essentially. So we can prove that if a Sigma protocol is secure, then its Fiat-Shamir transformation is secure as well, now in the quantum random oracle model. And again, you can plug in your favorite notion of security, and it is preserved without any degradation.
And again, you're saying you are not overcoming a possibility result, but unconvincing impossibility result.
Yes. So as a small caveat is that our security reduction is slightly less tight. So we get a quadratic loss compared to the linear loss in the number of queries that we have in the classical statement. Also want to point out that in independent work, Lia and Sandry, they showed the same kind of result, the security of the Fiat-Shamir transformation, but they have a much worse security loss of order q to the 9. Okay, so first I want to give you a bit of intuition.
Is there hope for Q, or there is a limit there?
Sorry?
Is there hope to get Q?
I'll say something about that on the last slide. So first I want to give you some intuition for why this result may indeed be true, or this kind of result may indeed be true. So I'm going to start with a natural approach where I recycle the classical reduction and I deal with this issue of this query being state by performing a measurement on that state. Well, I've said this is problematic because this measurement disturbs the state. And if you look at what exactly the prover may do, there is actually a way for the prover to perform a measurement on the answer that he gets from the oracle to check whether his query got measured or not. And so if he's nasty, then of course he may abort and you have a hard time. So at first glance, that seems to completely kill this approach. Well, or if the reduction measured his query, yes. So he can actually figure this out. So at first glance, this seems to completely kill this approach. However, if you sort of look closer in what exactly he has to do, how he actually has to measure the answer in order to find out whether his query got measured or not, then you see if he performs this measurement, well, he finds out whether his query got measured or not, but he's not going to learn any information about the hash, about the oracle, about the hash function with that query. But of course, in the end, he has to learn some information about the hash function. He has to learn h of a in order to be able to produce a valid proof. So we expect that there must be at least one query where he does not perform this check, but instead where he learns, well, one evaluation of the hash. And so if you're lucky enough to catch him there, we should be fine. Now, this is only intuition. It's only sort of one particular strategy for the prover. So the big question is whether you can turn this into a rigorous proof. Well, the answer is no. At least we didn't succeed. But we succeeded to turn, well, a slight tweak of this reduction into a rigorous proof. And the tweak is somewhat counterintuitive. According to the intuition that I've just given you, it actually seems to make the reduction worse. But then somehow, by magic, it allows us to come up with a rigorous proof. The tweak is simply to not use the reprogrammed oracle from that query on, where we sort of steal the first message, but instead we use the reprogrammed oracle either from that query on or from the next one. So we sort of toss a coin, and depending on the outcome of the coin, we do as before, or we actually wait one more step, and only from then on we use the reprogrammed oracle. And I have no understanding for why this should be useful, but again, turns out that it allows us to do the math. Yes, exactly, yeah. But why sort of this tweak allows us to come up with a proof and the more natural approach doesn't work? You have no understanding about that.
Can you say why? Is there intuition for why the other thing doesn't work?
No. No. Well, at least I don't have any.
Okay. So can you say again what you're doing? I didn't understand what you explained now. Can you say it again? What is this new thing that you just said that you read?
So right, I choose this query, pick this query, where I then sort of get the first message from. And then, now what in the original approach or in the natural approach, sort of from this point on, from this query on, you would use the reprogrammed oracle.
What do you use reprogrammed oracle in the random setting? Like you use like a...
Well, it's a random function, except now that at the point A prime, I set the value of h to be c prime. So, right, I mean, if I use the reprogrammed oracle on this query, I will actually answer with c prime, right? But I'm saying I'm not going to do that all the time. I'm only going to do that with probability 1/2. And with probability 1/2, I use the original h here. And only from the next step on, I use the reprogrammed oracle to answer queries. Okay, now I actually want to walk you through the proof. So I'm going to shift gears a bit, going to get a bit more technical, and it's also fine if you cannot follow every single step, but still I want to show you the proof because it's actually, after all, not too hard how the proof works. Also, I understand that most of you are now quantum experts. I'm not going to give any introduction to quantum, but then in the end, quantum is just linear algebra, and I assume that most of you know a little bit of linear algebra. So there we go. So I have to start with some preliminary observations and introducing some notation. So first, using standard reasoning, we can assume that P only performs measurements. Whoa, yeah, there's more to come, you see. So we may assume that P makes measurements only at the end. Also, we may assume that P outputs next to the proof consisting of A and Z. He also outputs the hash of A, right? You can always do that just by making one more query to the oracle. Okay, I've introduced some notation, so I'm going to call phi I the vector that describes the state during query I. So when the query was posed, but before the answer was provided. With phi 0 and phi q being the extreme cases, phi 0 being the original starting state, phi q being the final state on which the measurement then takes that produces A, H, and C. I'm going to denote by U from I to J the unitary matrix that describes the evolution from, well, step I to step J. And then, that's a bit of an uglier beast, I fix an arbitrary but fixed A prime. Think of A prime for the moment as what I want A here to be. I have to do that for technical reasons. And then I define this projection which describes a measurement acting on this state here, which measures, like P does, A, H, and Z, but in addition it does some checks. Namely, it checks whether A is what I want it to be, A prime, whether H is what it's supposed to be, namely the hash of A, and whether Z is a valid response, whether Z is accepted by the verifier. And to simplify notation, I'm going to write pi from I to Q, well, sort of everything that happens from query I on. I'm going to call this the continuation of P from point I onwards. Okay, now with this notation, I can write the probabilities I care about, well, in the language of linear algebra. Namely, the probability that the prover is successful, the original prover is successful when I additionally require A to be what I want it to be, as this square norm of this vector here. Now, let's say it's a square of a vector. Well, that's by the axiom of quantum mechanics, that Born's rule. This you just have to take my word for it. And well, this is just the vector that you get when you sort of run this procedure, when you run P and you do this sort of enhanced measurement at the end. Now, the probability we want to lower bound is the success probability of P prime, which is given by this beast here. It's a bit complicated looking, but look how it captures how P works. That's sort of the state at query I. Then ape measures this query and it checks whether the outcome A is what we want it to be. Then depending on what B is, and B is randomly chosen, we do one more step with the original H, or we continue with the reprogrammed oracle from that point on. So here is sort of this, we do one more step with the original H or not, and then we continue with the reprogrammed H. Of course, what I want is that this guy, if this guy is not too small, then this guy should not be too small. So I want to prove this kind of inequality, well, maybe up to some loss. Now, that's what I'm going to do. Okay, for that, I'm going to start with this vector here. This vector captures the state at query I, and then I complete things with the reprogrammed oracle H prime. Okay, by linearity, I can decompose it like that, just using the fact that A plus I minus A equals I, the identity. And then I can write this, well, continuation from I on as sort of one more step from I to I plus 1, and then continuing from step I plus 1 onwards. Okay. Now the crucial observation is that I minus A, that's a projection into orthogonal complement of A prime. So the U here acts on a superposition of all possible A's except A prime, except the one point on which H prime and H differ. So I can replace one by the other. Can multiply this out, observe that U from I to I plus 1 just upgrades phi I to phi I plus 1 here. Okay. Now, probably you're already lost, completely unclear where I'm heading, but sort of note that sort of with these just few simple transformations, I was able to introduce the terms I care about. Here I have the term capturing running P up to query I, measuring the query, completing things with the reprogrammed oracle. Here this term captures running P up to query I, measuring the query, doing one more step with the original H, and then completing things from there on. So I'm on the right track. Okay, so the next crucial observation is to see that this term and this term on the left and the right-hand side of the equality are the same, except on the right-hand side, the index I is incremented by 1. So this means if I add up this equality over all choices of I, ranging from 0 up to q minus 1, many of these terms are going to cancel out, right? I mean, this term with I being 1 equals this term with I being 0. So they're going to cancel each other out. So the only terms that survive are the extreme cases here when I is 0 and here when I is q minus 1. And the other two terms here I just add up. And the sum I can write slightly more compactly in this form. Okay, we're getting there. So next thing that I'm doing is I apply norms, triangle inequality, and rearrange the terms. Right, so this beast here just comes from here, this one comes from here, and this one comes from there. And I mean, the equality again is just triangle inequality. Okay, then I'm going to have a closer look at this term here. So phi q here is the state produced by P when interacting with the original oracle H. But then the pi H prime here performs a measurement on this state to obtain A and H, and then it checks whether A is what I want it to be and whether H is what it's supposed to be, namely the hash of A prime. But now the hash with respect to the reprogrammed oracle, which assigns a random value to that point. So this probability of happening, the probability of this check working out is small, is negligible, which means that the norm of this vector is small, so I can ignore it. And I'm essentially there. I have to divide by 2q to get the sum into an expectation. I square both sides. I apply Jensen's inequality to get the square inside the expectation, and I'm almost there, right? On the left-hand side, I have exactly what I want. On the right-hand side, I have almost what I want. The only difference is that I have here H prime. What I want is H, but I mean, if H is a random function and H prime is this random function reprogrammed at one point by a random point, well, it's also just a random function, so an expectation or an average over these choices, yeah, there's no difference between H and H prime, so there's no difference between these two states. And well, and that completes the proof. And I mean, note, that's sort of the full, rigorous proof of our main result. No cheating, no oversimplification, almost no cutting any corners. So that's the proof. Yeah.
I don't know, is it a good intuition, so why this could work? Because you're saying, in general, the prover can kind of check if you're trying to measure something, and by randomizing it between the step and the next step, and choosing random step, he doesn't really know, I mean, this is where this geometric sum comes in. He doesn't really know, whether or not you're going to measure, so he cannot like completely measure it.
No, I mean, if thinking about this kind of strategy of the prover to, well, as often as possible, try to figure out whether his query got measured or not, and only only in one query he asks for the hash of H, well, then it's actually better to reprogram the hash function at that point and not wait for the next day. So no, I really don't have any intuition. Yes?
So at the beginning you showed this particular strategy with the proof measures, but then you said without this of generality, we can assume that the proof only measures at the end. So does it explicitly exclude this strategy?
No, I mean, well, I mean, this measurement of a query can always be delayed.
But he has to report.
It's not a proof measuring,
No.
The A operator is a reduction measurement where it's not the prover's code.
But also, right, I mean, this is just intuition, right? That's sort of one particular strategy that I can sort of understand and for which I see, I mean, the obvious reduction should actually work.
Just the two statements, like having a strategy with the proof measures, and that's important.
I mean, he can always delay this measurement. He can always, I mean, that's sort of basics of quantum computing. You can always delay this measurement.
But Tristan was saying he has to respond to some classical...
You can always sort of...
Because it's
No, no. I mean, the prover only outputs something classical at the end. All the queries are quantum or superposition. So if you think of the prover doing a measurement and doing then one or another thing in the next step, depending on the measurement outcome, you can always not do this measurement then, do these two things in superposition and do the measurement at the end. We can discuss this offline if you want. I mean, it's not really relevant, right? Because the proof anyway doesn't rely on this intuition or this choice of prover. Okay, so the implications for signatures are then in line with what we have classically, which, let me just emphasize, sort of a critical point here is that we need the Sigma protocol to be a proof of knowledge against quantum dishonest provers, and this is still a bit of a tricky thing. That's sort of now sort of the bottleneck when it comes to proving security of signature schemes in the quantum random oracle models. In the last maybe 3 minutes, 5 minutes, if the chair is very generous, I want to say a few words about this issue. So the proof of knowledge property is formalized by means of the existence of an extractor that is able to extract a witness from any successful prover. And usually this is done by rebinding per prover. But this is problematic in the quantum case because measurements are destructive, measurements are irreversible, so we cannot rebind the prover in general if it's quantum. As a matter of fact, so far, the only known protocols for which we knew how to prove that they're a quantum proof of knowledge were protocols that satisfied some additional technical requirement referred to as having unique responses, which means, as the name suggests, that for every first message, every challenge, there is a unique response that the verifier will accept. Now, the intuition for this to be useful in this context is that if the response is unique, then measuring it doesn't disturb the state. But the caveat with this property is that for many examples, it's not satisfied. In particular, for the languages that we care about in the context of post-quantum crypto, this property is usually not satisfied. On the other hand, if we think of a computational version of this property, where we only require it to be computationally hard to come up with two responses for any given first message and challenge, it is known that in general, this property is not good enough to conclude the protocol to be a quantum proof of knowledge, even if we would be happy to settle with a computational version. So what we show is that we can relativize this negative result by introducing a strengthened variant of this computational unique responses property, which is defined in the spirit of Dominique's collapsing property. And we show that if a protocol satisfies this strong variant of computational unique responses and is special sound or more general T sound, then the protocol is a quantum proof of knowledge. Now, caveat is that this stronger version is still something that is in general hard to prove, but there are sort of different reasons for why, nevertheless, it's a good step into the right direction. Okay, concluding and also comparing again with the work of Lee and Sandri, in both these works we show, we show in our work, they show in their work, a particular extract and reprogram technique in the quantum random oracle model, which immediately applies the security of the Fiat-Shamir transformation in the quantum random oracle model. We lose a factor q squared, and Lee and Sandri, they lose a factor q to the 9 in this reduction. It immediately implies that if a Sigma protocol is a quantum proof of knowledge, that the Fiat-Shamir signature is secure in the quantum random oracle model, of course, as well. And again, both these works introduce a new and stronger notion of computational unique responses property and show that together with a standard special soundness or T soundness implies quantum proof of knowledge property. And together with known results on the collapsingness of the random oracle, we then immediately can conclude the security of the Fiat-Shamir signature scheme you get from Sikaboo, for instance. Again, in the quantum random oracle, of course. And then finally, in our work, we conjectured, while Lee and Sandri, they introduced some additional machinery which then allowed them to prove, for instance, as an example, that the sigma protocol underlying dilithium satisfies this new notion, and therefore dilithium is now also known to be secure in the quantum random oracle model. So dilithium is another signature scheme in the NIST competition for post-quantum secure signature schemes. And this is my last slide with some obvious open problems and future directions. And I just want to say something about the first one, sort of coming back to your question about this Q-squared loss. So we think this Q-squared loss is optimal, is the best that you can get. So we have a bit of a blueprint of how to prove that using a Grover kind of attack, but we still have to work out the details. So if the organizers organize next year, again, such a lower bound workshop, I might then actually be able to give a proper lower bound talk then. Thank you. Okay.
So is there any abstract technique or abstract reprogramming theory that you have? No? So I mean, you reprogram the random oracle at some point, and then you still hope that the adversary doesn't recognize this, but you do a bit more, because you use that somehow for the verification equation. So is there anything abstract you can give us to work on? Any tool?
Yeah, I mean, sort of this reprogram technique works, somewhat more general than just in the context of Fiat-Shamir signature. For instance, it works if the output at the end of the proof or algorithm is also quantum, right? Here, I mean, in the end, you care about the classical output, the non-interactive proof, but the same technique works if the algorithm outputs some quantum state here that satisfies some relation with the oracle. I mean, that's sort of the crucial thing, that it produces some output that has some specific correlation with the oracle, and what we can show is that, yeah, we can reprogram at one point.
How different is your proof from Mark's proof? I mean, is it like he does something similar, just lost, or he's reprogramming?
So our proof is 1 page. His proof is, I don't know, 3-4 pages. No, I mean his technique. He uses his compressed oracle techniques from his upcoming crypto paper. Yes, I mean the technique is very different, completely different. Yes.
And how's it different from RSA signatures? Hash and sign. I'm looking at other signatures where you do the previous papers. I forgot the statement. Which prove security of not RSA signatures, obviously, but this full domain hash.
Yeah, I don't know. I haven't looked into that yet.